Hello, Honors Chemistry, and welcome to practice from the outline covering up to section 10.5. So in the previous video, we talked about how to draw Lewis structures. We talked about the rules for how to draw Lewis structures. Now let's do some practice. So obviously, we'll need these rules, so you should have yours, and you should refer back to them as we do the practice. You need your periodic table, so we need to have something to look at, so we can count our valence electrons. And then we're just going to do a bunch of practice. You'll probably want to put these on the back of a sheet so that way you'll have them as a point of reference as you go on and do your independent practice later. If you are super lost, right, and if the skill builders in the outline just went way over your head, then you probably just want to watch and listen and then go back and watch it again, okay? If the skill builders went really well and you're like, wow, this was so easy, then you may just want to pause, draw the structures, look at the solutions, and then sort of see how it's going and see how much you need to listen to, right? Just stuff to think about. Okay, Lewis structure practice. So here we're going to draw Lewis structures for potassium chloride, right? So first, what do we need to do probably? Right, preliminary step that we didn't write in the rules is we need a formula, okay? And then if we go back to our rules, right, we wrote it down here, but really we could put it up here as a preliminary step. We should also ID the type because that's going to help to guide us, right? What kind of compound is this? Right, this is an ionic compound, meaning is there going to be sharing of electrons? No, right. It's going to be a give and take such that we form cations and anions. So, let's go look at our Lewis structures, right? Potassium has how many valence electrons? Right. Chlorine has how many valence electrons? Right. So then, if I think about how this works, right? And here, like these two things should feed off of each other, right? We already know that this is the formula, right? And we know this is the formula because this has a plus charge, this has a minus charge. So, in order to become a plus charge, what has to happen? Right, it's going to give its electron over here, which means that now we have K plus and Cl minus, yes? All hanging out together. Next up, potassium oxide. So here, and we would think, oh, yep, this one's also ionic, right? And so we would do the same thing, right? We have K, we have oxygen, and then we would say, well, right, what's going to happen is potassium is going to give one electron, and then I'm going to have two potassium ions with a plus charge, and then one oxygen that's going to have its full octet. Now, here, right, don't forget that once we lose those valence electrons, we're not going to draw 8 here, right, because we're going to show that its original valence is empty, right? Now it does have a full valence because, right, its valence is now technically the shell inside. Yeah? Make sense? All right, next up. Methane. So first we need a formula, right, CH4. And then we're going to distribute my atoms, right? Which one's central? Right. By the way, central atom, 9 times out of 10, is the one that's written first. Just, to help you out. So we have our carbon. We're going to distribute my hydrogens. Now, again, Lewis structures are just a model for bonding, okay? A model for bonding, which means that if you really want to put all of your hydrogens down here, it doesn't matter. It's the same exact thing, right? As long as everything is bonded in the same way, okay? So, finishing these out, right, we arrange our atoms, and then we're going to, right, count our valence electrons. Carbon has how many valence electrons? Right, 4, and then hydrogens have 4, we have 4 of them times 1, so we have a total of 8 valence electrons. So, now that we've done this, we're going to distribute our electrons first by drawing bonds, right? Because everybody has to get bonded if they're all going to make a molecule, right? So I've distributed 2, 4, 6, 8 electrons, which means I have 0 electrons left to work with, okay? Because my entire structure can only have as many valence electrons as we started with. So then we count carbon, right? Carbon has 2, 4, 6, 8. What about my hydrogen? Right, hydrogen obeys the duet rule, and hydrogen has access to 2, 2, 2, and 2, which means that yes, this structure is complete. We've done our double checks, and it's all done. Here, by the way, right, like if we wanted to, it's exact same thing. These two structures say the exact same thing, and either is completely correct. Okay? All right, next up, we have carbon tetrachloride. So what's this formula? Right, CCl4. And so again, central atom. And we're going to distribute my chlorines. And then, right, we're going to count our valence electrons. So we have 4 again. And here we have 4 times what? Right, 4 times 7. So we have 4 times 7, which is 20, what? 28 plus 4. So we have 32 electrons to work with. So step 1, we're going to bond everything. And that takes up 8 electrons, which leaves me with 2 and then 6, and so 24. And so this chlorine has access to how many right now? Right, has access to 2. So it needs 6 more. Yes? This one, same scenario. Symmetrical structures are nice that way, right? And so if I use 6 times 4, that's a total of, right, which means I have 0 electrons remaining. I've used all my electrons. Now we go back and do our double checks, right? First, did we use the right number of electrons? Here we have 8, 8, 8, 8 times 4 is 32, right number. And then chlorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Yes, we're done. This structure is good. Make sense? All right, next up. Carbon dioxide formula is, right, CO2. Again, carbon is central, oxygen, oxygen. Count our valence. This is 4. This is 2 times 6, which is going to be 12 plus 4, so I have 16 electrons to work with. So I'm going to draw my bonds, okay, and I burned how many? Right, that cost us 4 electrons, so I have 12 left. So I'm going to start filling octets, right? So where do you want to start? Let's start here. 1, 2, 3, 4, 5, 6. And then symmetry, right? So 1, 2, 3, 4, 5, 6. So that's 12 electrons. All right, we used all of our electrons. Woohoo! And then now what do we do? Right, we go back and we double check, right? So 2, 4, 6, 8, 10, 12, 14, 16. Okay, we used the right number of electrons. This oxygen has 2, 4, 6, 8. Great. This oxygen has 2, 4, 6, 8. Great. This carbon, though, has access to, right, only 4, which means, right, this is one of those scenarios where we have to redistribute. So what that means is we have to form double and or triple bonds as needed. So what I recommend is you can't exceed the total number of electrons, right? So I can only have this many. So what I would recommend is you erase a pair before you start trying to draw new bonds, right? So I took away a pair, and now I can draw a new bond, right? So now this oxygen has 2, 4, 6, 8. This carbon now has 2, 4, 6. What seems like a good solution next? Right, let's go ahead and redistribute one of these pairs. Now, 2, 4, 6, 8 for oxygen, 2, 4, 6, 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for carbon. We do meet our criteria, yes? All right. Next up, nitrogen. What's its formula? Right. N2. So no central atom, right? It's just N2. How many valence electrons do we have? Right, 10. So we're going to draw a bond. Then we'll subtract that off. That gives us 8. So 2, 4, 6, 8. What do we notice? Right, this nitrogen does not have an octet, so we're going to start redistributing, right? So we'll put that there. Do we have octets? Nope. All right, so one more. Now 2, 4, 6, 8, 2, 4, 6, 8, and total of 2, 4, 6, 8, 10. So the structure is good. We meet all the criteria. All right, next up. Arsenic trichloride. Arsenic trichloride. And so then again, central atom, trichloride, count our valence electrons. Arsenic comes with, right, 5. Chlorine comes with, right, for a total of 26 electrons to distribute. Yes? All right, so bond, 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 minus 6 leaves us with 20. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that's a total of what? So 3 times 6 is 18. And what do we notice? Right, arsenic still needs a pair, and now we have 0. So we go back and double check, right? Here is 8, 8, 8. That's 24, 25, 26. So yes, we used the right number. Chlorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And arsenic has 2, 4, 6, and 8. So yes, we are good. We did it correctly, probably. All right. Finally, we have arsenic pentachloride. This formula is, right, ASF. Oh, no, I did chloride. Oh, why do I keep writing that? Oh. All right, so arsenic at the center, chlorine, 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 chlorine. Counting valence electrons, right? This one has 5. This one has 5 times 7, so 35. So we have 40 electrons to distribute. So let's go ahead and draw our bonds. So if we drew that, we used 10, which leaves us with 30. Next up, right, fill octets. So I did 6 times 5. So I used all 30. And now we'll go back and do our double checks, right? So chlorine, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, chlorines are good. Arsenic has 2, 4, 6, 8, 10. That's really weird. Let's count our electrons, right? If we have 8 times 5, that's 40. So I used the right number. And so we would stop and think to ourselves, is this okay? And you would conclude, right, you would conclude that yes, it is okay, because if we take a look at a periodic table, arsenic is indeed in period 3 or greater, so it is capable of having an expanded octet if that's what the number of electrons calls for. So this is our practice on Lewis structures. If need be, if some of these are fuzzy, go back and watch it again, right? Make sure that you are good here with these structures, and then